The electric field is a very interesting concept, and fields in general are discussed a little bit in Physics 1 due to the gravitational field of the Earth, but that situation is not very dynamic. Whereas the electric field is very dynamic. And since we started talking about electricity, you probably wondered when we were going to start using the V word, as in volts. And we're just about there. So we start off then thinking about what an electric field represents. So when we were looking at electric forces, you notice that it takes two charges to make a force. And that goes back to the original thing of force is an interaction between two things. And that's how Newton's third law works, is where you have two things, they both feel the force, but they feel it in opposite directions. But then the question comes up is that, well, what if you just have one charge? What does it do? Does it do anything to the space around it? And the answer is yes, it does. So it does impact the space around it, especially if it's a large charge. Now, compared to gravity, we can do the same thing. The Earth is large enough to have a considerable gravitational field. But all things can interact with gravity, all things that have mass. And so you yourself, you have mass, but your mass is not really big enough to generate a gravitational field that anybody would notice. But you can feel a gravitational field because you have mass. So it's the same thing with charges. Charges will feel a force when they're placed in an electric field, and the electric field could be caused by other charges, or it could be caused by a distribution of charges. So the electric field is the force that a charge would feel if it was there. So that means that for a point charge, it sets up an electric field that has a magnitude of just kq over r squared. Now you'll notice that in the electric field, there's capital Q, and then the force on a point charge in that electric field has a little q. That again goes back to what I was talking about with your mass compared to the Earth's mass. So the Earth's mass is big enough to generate a gravitational field, and your mass feels it. So the reason why we use capital Q in the formula for a point charge is that that charge is big enough to generate an electric field. And when we put little q in there, little q is big enough to feel the force, but it's not big enough to really alter the electric field significantly. So we can represent these field lines, which are, for all intents and purposes, are lines of force. And they will radiate outward because if we put a positive charge anywhere near there, a little test charge, just like you're a test mass to detect the presence of gravity, and put a test charge there, it's going to feel a force away from the positive charge. So that's why the field lines go away, and that's why the field lines go towards negative charges. And roughly when we're drawing them, the number of field lines can sort of represent the magnitude of the charge, with field lines being stronger where the field lines are closer together. But we don't really see that representing too much. So now here's a different distribution of charge. These are two conducting plates that have equal and opposite charge placed on them. And this is really convenient because this generates electric field lines that are parallel to each other, except at the edges. And so that makes a uniform electric field. That means the electric field is constant everywhere inside this region. Right, so here's a nice summary, and there are lots of different applications of electric field. Right, so in this photo copy machine, as the image gets scanned, then light's focused on this charged roller, and then as the roller goes past, it's going to pick up toner that's proportional to how much charge got deposited on it. So let's take a look at a simulation to just sort of bring this to life. Let's grab a positive charge, and we'll bring out an electric field sensor. And we'll turn values on so that you can see what the numbers look like. And we have electric field lines radiating outward. Now, if we look at the units for electric field, this is volts per meter. Again, gravitational field of Earth, 9.8. Back in Physics 1, we called it 9.8 meters per second squared. But then later on, we started referring to it as newtons per kilogram. So we can see the closer we get to the positive charge, the electric field really blows up and is actually sort of a singularity. That means that this 1 over r squared is going to get really huge when r is very small. And then out here, it's actually kind of hard to detect. Now, let's take a negative charge and place it in there. And in fact, let's place 2 there. So with my electric field sensor, you can see that the electric field in between the 2 charges is really strong. But there is a region out here where actually it approaches 0. Right, and that's one of the things that you can solve for, is find a place where the electric field is equal to 0. Okay, now let's explore some different distributions of charge. So let's pile them up. From a problem-solving point of view, I'm going to turn the grid on so I can get them aligned nicely. For the problem-solving point of view, electric field is really similar to electric force. So there, it is vectors. They're going to add like vectors. And now as we sort of pile up this line of charge here, you can see that the electric field at one particular position is actually the sum of the contributions of all the other charges. But if they're all lined up like this, then in this case, their y components have canceled out, and so we only see x components. And if we go ahead and sort of complete this charge distribution by placing more negative charges on it, then you can see that that electric field pattern that we had discussed before starts to take shape. And so the electric field is very uniform here. I don't know where this little guy is there. Put you away. Right, it's very uniform, not only inside, but on the outside as well. So up we go, the electric field gets really strong. And now right in this region, well, it's not that consistent, but theoretically it should be pretty much a constant in here. All right, well, let's go ahead and grab one more thing. We'll put that sensor off the board there. And then this is called an equipotential drawer. So I'm going to find a place where it's about 10 volts. Okay, let's choose 11. If I draw this, this is going to show me the set of all points that are at 11 volts. And then let's see if we can find 0. Okay, that's pretty close. Right, and then if I pick some other number that's halfway in between 11 and 0, like maybe 5, like in here, you can see that inside this line of distribution, they're pretty equally spaced. So equipotential surfaces are locations that all have the same voltage. And voltage is potential, electric potential, kind of like potential energy. And so if you were to go hiking, say, and you wanted to pick what kind of route that you would choose up a mountain, you might look at a topographic map. And let's do that right now. I'm just going to grab a topic. Let's go topographic map of Camel's Hump. All right, great. Yeah, Mount Mansfield State Park. Okay. Terrific. So if we zoom in a little bit, and here's the hump right here, which Samuel de Champlain called Crouching Lion. There's a nice ridge over here, and where's Robbins Mountain? It's not going to be too far away, I don't think. Yeah, here, there's an observatory tower here. I think that's still there. Probably put some cell phone stuff on it. Anyway, and there should be a shelter around here somewhere. But anyway, here's the summit. And so we zoom in on the summit and we can see that, yeah, it's just slightly over 4,000 feet, but these contour lines are lines of equal elevation. And so if we were hikers and we were taking a look at which way to go up, don't really see any trailhead. I think there's an old abandoned airplane on the back, unless it's been moved since then. But at any rate, places where the lines are spread out means it's relatively not too steep. But right here on the southern edge, it's practically a wall. So the equal potential lines, or the lines of equal elevation, are very close together. And that means that the pull of gravity down these lines is pretty strong here, whereas the pull of gravity down these widely spaced lines is going to be weaker. So you can almost think about electric field as the steepness in a world of charge. And so in this world of charge, it's the steepest right in here. All right, well, I hope that helps to clear some things up around electric field.